Okay, Class C, I am very sorry that we weren't able to get to this today and that you're having to devote a little bit of extra time to a video, so I'll be as quick as possible. Chapter 9 is all about sequences and series. It is the most tested BC topic, and so you're going to have 2 assessments in the chapter, and they will be pretty important. I can't stress it enough. We only have 2 chapters left, this one and then polars and parametrics. So we're on the downhill. So let's first of all talk about a sequence versus a function. I mean, it says an infinite sequence is a function whose domain is the set of positive integers. And how that differs from an actual function is if I have f of x equals x squared, then you really don't have any limitations. You can put any number you can think of. You can put in integers, you can put in rational numbers, you can put in irrational numbers. Heck, you can even put in imaginary numbers because we know that I squared equals -1. However, when I write a sub n equals n squared, it's still in the same sense of whatever I put in for n, I'm going to square it, but the domain is limited. You don't have a half term. You don't have a pith term. You don't have an ith term. You have a first term, a second term, a third term. So think of your ordinal numbers. So if I was to write out the first 5 terms of this sequence, a1 would be 1 squared, a2 would be 2 squared, which is 4, a3 would be 3 squared, which is 9, a4 would be 16, and last but not least, a5 would be 25. So you just put the ordinal numbers in, or the positive integers 1, 2, 3, 4, and 5. Okay? One thing that the little worksheet that I gave you at the end of the quiz is having you practice is looking at the numbers. So if you saw 1, 4, 9, 16, 25, ... You might look at those and go, oh, those are all squared. So that would be a sub n equals n squared. There's also alternating series, which they go from positive to negative. So if I change this up and went 1, -4, 9, -16, positive 25, how do you get your terms to alternate signs? And the most traditional way of doing it is putting a -1 and then your n squared. So you kind of keep the alternating piece separate. If I put in 1, it looks like my first term is positive, so I need an even exponent, so my product is positive. So usually we either put an n or an n plus 1, and in this case I would put an n plus 1 because when I put in 1, I need it to be squared. When I put in 2, I need it to be odd, so I get that negative second term. I was telling the B class, just kind of made a joke, if you really want to impress someone with an interesting way to make something alternate, you could do it with this, cosine of pi n times n squared. And when you put in 1 for n, cosine of pi is -1, so you've made that first term to be negative, and then 2 pi would make it 1, and then 3 pi would make it -1, and so on. You'll see this in the textbook every once in a while, so I don't want to throw you off. So going from being able just to write this nth term, so the a sub n from a given sequence, we're also going to talk about convergence, and that's probably the biggest word that you're going to see used throughout this chapter. So if we say that a sequence is convergent if the limit as n goes to infinity equals L, where L is a finite real number. Okay, so some things that are not finite. Well, obviously, if your series is going to infinity or negative infinity, that's not finite. It's also, you could come up with a really silly one that goes 1, 0, 1, 0, 1, 0. And where it's predictable It's not going to a single finite number. It can't make up its mind. So there's really two big egregious non-convergent, which we would use the word divergent series, and that would be ones that are going to either positive or negative infinity, and those that just can't make up their mind where they're going. So if you're talking about whether a sequence is convergent, we're going to take the limit as n goes to infinity of our defined sequence. And you can use the very same rules that you use for x when we're talking about functions whose domain is much broader than that of a sequence. In this case, there's your Bobo button eats DC. You've got equal power top and bottom. You reduce the coefficients. And so we would say this converges to 2. All right? The next one, factorials. We're going to have to get used to simplifying factorials. They're going to come up throughout the chapter. It's very algebraic and kind of fun to do once you get the habit of it. But it's not going to be where you have numbers. You're not going to have 3 factorial over 4 factorial that much. You're going to have them in terms of n. So how do you simplify a factorial? Well, 4 factorial is just 3 factorial times 4. You cancel the 3 factorials, and you get that this simplifies to 1/4. So we're going to use the same thought process over here. N plus 2 factorial is just n plus 1 factorial times n plus 2. It's all the ones up to that, and then plus 1 more over n plus 1 factorial. The n plus 1 factorials cancel. N is going to infinity. However, n is in the numerator. So this is going to infinity, and we would say divergent. This last one I put in because we haven't used our friend L'Hopital in a while. We do have infinity over infinity here. This is an indeterminate form of infinity over infinity. So we can take the derivative of the numerator, take the derivative of the denominator, and reevaluate. I want to kind of go off track here just a minute and talk to you about if I was a college professor, I would make you come over here to the side and do this in terms of x, because you can't take the derivative of non-continuous functions, and a sequence is not continuous. You are jumping from 1 to 2 to 3. There is nothing continuous about this. If you graph a sequence, you get dots. If you graph a function, you get curves and lines. So because it's technically not cool to take the derivative of something in terms of n, I'm going to come over here and do it in terms of x. I will not count off if you do not do this. I just want you to know that I'm cutting us all a little bit of slack, but I did want to tell you what you need to do. The derivative of the numerator is 2x. The derivative of the denominator is 2x divided by x squared. So remember, the derivative of a natural log puts the argument in the denominator and the derivative in the numerator. And this simplifies to x squared. And the limit as x goes to infinity of x squared is infinity. So we have another infinity and divergent. Let's see if I can pull up this other sheet for just a minute. So this was what I gave you after the quiz. And so you're just matching the sequences with their definition. And if we look at some of these, we should be able to tell what's going on. On A, this is going to negative infinity, so it would be divergent. On B, can't make up its mind, divergent. C, 1, 1/2, 1/3, 1/4, 1/5, ... I can see by looking at this, it's going to 0. If we go up here and find C, C is defined as a sub n equals 1 over n. And if you take a limit as n goes to infinity of 1 over n, you do indeed get 0. So this one converges to 0. Then we get a lot of like infinity, 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 so on, so on. Here's another one that can't make up its mind. I is 1/2, 1/4, 1/8, 1/16. It looks like what we have here is 1 over 2 to the n. And if you take an infinity limit there, you've got a constant on top, you've got an exponential on bottom. This one is going to 0 as well and will converge, okay? There are two specific types of sequences that you learned about in pre-calc. One of them is arithmetic. The other one is geometric. If I come down here and look, T is arithmetic because you can define it as a sub n equals 2n minus 1. In other words, I'm going up by 2. So 1 plus 2, 3 plus 2, 5 plus 2. And those are always going to be divergent because if your common difference is positive, it's eventually going to go to positive infinity. And if your common difference is negative, it's headed to negative infinity. The other one is your geometric, and looking for a specific geometric on here, I is a geometric series. It has a first term of 1/2 and a common ratio of 1/2, meaning that the first term times a half gives you the second term times a half gives you a third term, and so on. And we're going to talk about those when I go back to the other sheet, and part of your homework on the back side of this will have to do with geometrics. I was thinking there was another geometric on here. Let me see if I can find it. Here we go. Q. Q, the first term is -2. And the common ratio is also -2. And that's going, positive and negative and positive and negative, but it's moving further away, like it's going to positive infinity, negative infinity sort of thing. This is clearly divergent, not just because of the infinity aspect of it, but because it's getting further away from a value. S is also geometric, 1/3 times 3, 1 times 3, 3 times 9, 9 times 3, and so on. But you can see that this one is also going to infinity, and it's divergent. So what makes a geometric convergent versus divergent? We shall go back and talk about that. Okay, so a series is defined as the sum of a sequence and is either finite or infinite. It's used with notation. Usually when we say it's finite, we're just adding up a set number of terms, like 5 terms, 4 terms, and so on. The ones that we're going to deal with most this year are infinite series. Those are the ones that are interesting. And we just start off first term, second term, plus third term. So again, a sub n is defining the terms. S of n is defining the sum of those terms. Any series that's in the form of a r to the n, where a is your first term and r is your common ratio, if that r, if the absolute value of it is between 0 and 1, then you have a convergent series. And then if your absolute value of r is greater than or equal to 1, you have a divergent series. So it's pretty simple to see whether your geometrics converge or diverge. Remember, your arithmetics always diverge. I wrote this one for a reason. You'll see it like this a lot. Anytime you have a 1 on top, you could actually write that as 1/2 the quantity to the n, because 1 to the n is always 1. So when you look at this, r is 1/2. The first term is also 1/2. And so because your absolute value of r is between 0 and 1 with 1/2, then we can use the formula S equals A1 over 1 minus r, which is actually equal to 1. And so if we go 1/2 plus a 1/4 plus an 1/8 plus a 1/16 plus ... and I start adding these up, the sum of the first term is itself 1/2. The sum of the first two terms is 3/4. The sum of the first three terms is 7/8. The sum of the first four terms is 15/16. And from that, hopefully you can see that the sum as n goes to infinity is indeed 1. Looking at the second example, a sub n equals 5/3 to the n. Well, we go ahead and just grab it real quickly. 5/3 is r, and 5/3 is clearly greater than 1. Therefore, your geometric series is divergent. A sub n here, it's not as clearly defined as what your r is because 3 is to the n and 4 is to the n minus 1. On one like this, you'd want to split it up. 3 to the n, 4 to the first, 4 to the n, and then you can rewrite it as 1/4 times 3/4 to the n. So you clearly can see now that your r is 3/4. If you put in 1, what do we have here? We have 3 in the numerator and 16. So it's very important that that extra 4 gets considered in as part of the first term. And so your infinite sum is 3/16 divided by 1 minus 3/4. And so 3/16 divided by 1/4 is 12/16, which is 3/4. Okay, so that's really all I was able to go over with in B. I'm going to send this to everybody in case they want to take a look. The homework that you need to upload is the back side of the sheet that we were looking at with you identifying the sequences. Hopefully this helps. I will see you on Wednesday. Have a great rest of your day, and thanks for watching.